Potential can be defined as a sequence of changes in the membrane potential of an excitable cell due to opening and closure of different ion channels after the application of a threshold stimulus. This is the graphical representation of the change of the membrane potential when a nerve is stimulated. The membrane potential is going to change from minus 70 to plus 30 millivolts. So when the stimulus is applied on the nerve, initially there will be entry of the sodium channels, which causes the depolarization, and uh, at this point opening of the potassium channels, which is going to lead to the potassium efflux, and there will be loss of potassium ion that is going to lead to a repolarization. And we have different uh, other stages also, like stimulus artifacts, firing level, overshoot, after depolarization, and after hyperpolarization in an action potential. We're going to see them one by one. As I said, there are different phases, that is resting membrane potential stage. So here the inside the nerve, the potential is negative, and outside the nerve it is positive. So that's why the resting membrane potential is always negative inside the cell compared to outside the cell. The membrane is maintained in polarized state by due to the distribution of ions across the cell membrane, and some ions diffuses out of the cell along its concentration gradient, while non-diffusible ions, that is proteins, stay inside the cell. If you compare inside the cell, there are some negative ions, and because of which there will be uh, unequal distribution of the ions which is going to occur. And if you know, and we know that potassium concentration is high inside, and this tries to move out of the cell, and at the same time sodium concentration is high outside, which is going to try to move inside the cell. And the permeability nature for potassium is high, so sodium cannot compensate for that. So uh, the the negative inside will be more because of the potassium uh, efflux. As we said, sodium influx does not compensate for potassium efflux because the membrane at rest is less permeable to sodium than potassium. And also sodium potassium pump causes continuous pumping of 3 sodium to outside for each 2 plus potassium ions pumped inside. This also creates additional degree of negativity, and that is the basis for resting membrane potential. And stimulus artifact is when stimulus is applied, there is a brief irregular deflection of baseline due to the current leakage from stimulating electrode to the recording electrode, and the latent period is going to corresponds to the time uh, it takes to travel along the axon from the site of stimulation to the recording electrode. So this diagram showing the resting membrane potential, it is always maintained negative inside, positive outside. It is mainly because of the potassium efflux which occurs, and also there is because to compensate, the sodium is going to try to move in, but the potassium overrides that activity because it has a more permeability for the cell membrane. So the the inside of the cell, that is why it is maintained, it becomes more negative. And also sodium potassium pump, which tries to uh, pump 3 sodium out of 2 potassium, so that is also is responsible for some part of resting membrane potential. Depolarization, when the membrane potential reaches the voltage between minus 70 to minus 50, there occurs sudden conformational change in the activation gate of sodium channels, flipping into open state. That is, these are voltage gated sodium channels and has a 2 separate gates, activation and inactivation gate. Uh, as activated state sodium ions, they are going to move in. The tracing rises rapidly till plus 35 millivolts. Now inside the nerve cell becomes positive and outside the nerve it is negative. You can see, so when the voltage gated sodium channel, they are going to activate, so it is going to cause activation gate to open, so that is why sodium is going to move inside. Okay, and at 30 mmHg, the inactivation gate is going to close, and that is going to limit the entry of sodium, and it is not going to open until the resting membrane potential reaches back to resting membrane potential. And when some sodium enters inside the cell, okay, and it is going to lead to the threshold level, that is at threshold level it is going to open up the adjacent voltage gated sodium channels, and so this is going to cause a tremendous entry of sodium ions inside the cell, and that is going to lead to the massive change in the membrane potential. Okay, and the stimulation of adjacent voltage gated channels, is called as Hodgkin's cycle. That is, the change in the polarity is going to stimulate the adjacent sodium channels, and the causes the entry of massive amount of sodium ions is called as Hodgkin's cycle. Repolarization. After sodium channel has remained open for 10,000 of a second, it suddenly closes. At this point, the membrane potential begins to recover back to resting membrane potential. Repolarization starts with potassium efflux due to the opening of voltage gated potassium channels. A very important characteristic of sodium channel inactivation process is that inactivated gate will not reopen until the membrane potential returns to resting membrane potential. So this is the ionic basis of repolarization. At minus 35, the potassium channel is going to open, and this is going to lead to the potassium efflux, and so this potassium loss continues till the hyperpolarization state. After depolarization, at the termination of spike potential, potassium conduction is slowed down, and thus few milliseconds are delayed in restoring membrane potential. So this last phase of slow potassium efflux is called as after depolarization. And after hyperpolarization is where resting membrane potential is achieved by the active sodium potassium pump mechanism, which transport 3 sodium out and 2 potassium in. Okay. So after hyperpolarization occurs because of the delayed closure of the potassium channels, which causes the more negativity inside the cell because of the delayed potassium efflux, and by putting out some sodium outside the cell, it is going to bring back the resting membrane potential back to the normal. Okay. So that is done by sodium potassium pump. Okay. So this is the ionic basis of after depolarization. It mainly occurs because of the increased potassium levels outside, so that is why the potassium efflux is delayed, so that is why the repolarization process is delayed in this part. And hyperpolarization occurs because of the continuous or delayed closure of the potassium channels, and the resting membrane potential goes beyond the resting membrane potential, and then it is recovered by